Okay, so in this video we're going to be looking at distributions and just kind of some of the basic properties of a couple of the distributions that we can see. The first type, most basic, is frequency distribution, and that's just a way of like taking the data you have and organizing it into like a logical manner. And really, just like it says in the definition, they're values that you're plotting against the frequency of their outcome within the data set. So, for example, I have some sample data right here on resting heart rates. And so what we do is we're going to take that and we can say, okay, the first thing you want to decide is like what range, how do you want to distribute these values within the distribution you have. So I have them plotted in groups of 10 here. And notice that there's no overlap between the plots. And so it really, these are just as easy as going through the data and looking through and say, okay, what numbers do I have in my data set that range between 51 and 60? So there's one. Okay, so I have one frequency count of 1 for that range, and 61 to 70, there's 1, 2, 3, 4, 5, 6, 7 of those. So that frequency is 7. 71 to 80, there's 1, 2, 3 of these. 81 to 90, 1, 2, 3, 4. Oh, looks, I missed one. There's 4 of these. And then 91 to 100, there's 2. Okay, and you've got your frequency distribution, where this is my range of values. I notice that it's continuous, right? There are no breaks in my ranges from beginning to end. That's important. You can't skip a range value. You may have some in the middle that includes 0, and that's fine, but you can't exclude those, right? You need to be able to see everything from the bottom to the top of your range. And these intervals need to be equal, right? This is 10, this is 10, this is 10, this is 10, this is 10. Okay, so this is one way for me to look at this, right? I have all of this data, which might be hard to read right now, right? It's random, there's not a lot of order, but I can take it and within a frequency distribution, I can organize my data in a way that makes it easy for me to see what the distribution or what the plot looks like, or what the plot could look like. But let's say that this range, let's say that it really wasn't serving me, okay? Another thing that I could do is I could break up the range a little bit, right? So here, again, I'm starting at this bottom, but now I'm breaking it up into units of 5 instead of units of 10. Okay, so 51 to 55, I have 1. 56 to 60, I have 0. 61 to 65, I have 1, 2, 3, 66 to 70, I have 1, 2, 3, 4. And then 71 to 75, I have 1, 2, and so on, right? This would need to continue until I'd included all of the data within my data set. But you get the picture. And so this shows me a different picture than what I saw over here before. And so you need to be really careful how you pick these ranges, because it'll change your story a little bit, right? The distribution doesn't change, but the way that you plot these does change. Okay, so this is what a frequency distribution looks like. Next thing we want to look at is, and then both of these, so this type of data, right, this Now these heart rates, they're not really continuous, right? Because you can't have a heart rate of 61.5 beats per minute, right? Typically those are counted on whole numbers. But this type of quantitative data you plot in a histogram, okay? And we'll look at those in a second, right? So here's a different type of frequency distribution. So this is, this one we're looking at qualitative data, right? Categorical data. So you surveyed a bunch of people and found out what their favorite flavor of ice cream is. And so to plot this, right, it's kind of the same thing. Here I'm looking at, well, here's all the flavors that I have available. And so what are their frequencies? So I say, okay, well, let's start with chocolate. So there's 1, 2, 3, 4, 5, 6 chocolates. And vanillas, there's 1, 2, 3, 4, 5 vanillas. Strawberries, there's 1, 2, 3, 4 of those. Mint, 2. And butterscotch, 1. Okay, and then there's the frequency distribution for these. Now, the one thing that's really important is when you're thinking about this type of data is I ordered these totally randomly, right? And it ended up counting down, right? 6, 5, 4, 2, 1. But I could have put butterscotch first, right? Had I done this alphabetically, then butterscotch would have come first in the list. And then chocolate would have been next, right? And so this doesn't plot the same way, right? You can't make a histogram out of this. But what we can make is a bar graph. And we'll look at that here in just a second. So what's a histogram, right? So this is a graph that uses rectangles to represent the frequency of observations. Okay, so here's my frequency distribution from before. You can see all the different frequencies. You can see the ranges that I made, right? And now I'm going to plot this on a graph, right? So here on my y-axis, right, you're always going to put frequency here. Frequency goes on the y-axis, but I probably should just denote it with a capital F, right? So the frequencies go there, and then my ranges, or the resting heart rate, we'll just do it like that, HRH, is going to go on the x-axis. And now you need to decide how to distribute this. So maybe we'll call this 1, 2, 3, 4, 5, 6, 7. That fits. And then with my plot ranges, if I called this 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So you can kind of see, okay, my 51 to 60 is going to fit here, and that goes up to 1. My 61 to 70 has 7, so that goes all the way up to here. Notice there's these nice rectangles, and then 71 to 80 is going to fit into this section, and that goes up to 4. And 81 to 90 also has 4. And then 91 to 100 has 2. Okay, and so now I've made a histogram of this data. Now you might look at this and say, well, what's the difference between a histogram and a bar chart? Well, so histograms deal with quantitative or continuous data. And notice that my bars, they all share a common border, right? They're touching. Now, I didn't have any data here, but I could have maybe had some data way down over here. I mean, hopefully somebody's resting heart rate isn't between 20 and 30 beats per minute. But it's okay to have a loner, right? But your ranges have to have distinct boundaries that touch, because that's the nature of the data that we're collecting here, okay? So these are histograms. Again, it's just a way to kind of visually represent and look at the data that you have. So next are bar graphs. And so now the difference here is, again, this is going to kind of look like a histogram, but instead these bars are not going to touch. They can't touch because it doesn't make sense for them to touch. This data isn't continuous. It's just categories, right? And so it's like with this stuff, I kind of decide, well, okay, so I'm going to put something here, and so, I don't know, maybe let's put vanilla here, because it doesn't, right? Order doesn't matter. At least, I mean, this is nominal data, so it's not going to matter, right? Then maybe I'll put chocolate here, in this box, and then in this box I'll put strawberry, and in this box, I know that's hard to read, but mint, and then in this box, let's do butterscotch. Did I get them all? We'll see. Okay, and now I want to plot my actual bars. So for vanilla, hold up, 1, 2, 3, 4, 5, 6. Again, frequency is over here, so this is F for frequency, and then my categories are here, right? Or this is the ice cream. Okay, and so then for vanilla, I'm going to put a bar up to 5. And then there's a gap. Chocolate has a bar that goes up to 6. And then there's a gap. Strawberry has a bar that goes up to 4. And then there's a gap. Mint has a bar that goes up to 2. And then there's a gap. And butterscotch has a bar that goes up to 1. Right? But what you need to notice here is that there are these gaps, right? Gap, gap, gap. This is not continuous data, right? These bars, they're not going to touch, right? That's why this is a bar graph and not a histogram. Because again, I can order each of these however I want. There is no set way to order this. I mean, even if we were dealing with ordinal data that had an order, right? If you were looking at, if you wanted to do a bar graph of, let's say you were studying groups of young people and you wanted to know what grades they belonged in, right? That's ordinal data, right? First grade, second grade, third grade, fourth grade, right? There is a natural order to that. But even those still would have gaps in between them because the data you're collecting about it isn't continuous. Like resting heart rate can be kind of thought of as continuous data, okay, or something like that. So these are what bar graphs look like, and these are kind of how they're made. And again, all of this is these are just different ways for us to visualize the data that we're working with, right? Get a picture. We're looking at the big picture here because often just looking at either frequency distributions or the raw data itself, like you can't see the patterns. We want to bump up to be able to see those big pictures. Okay. So the next type of plot that we want to look at that you'll see in the readings and in the homework is the stem and leaf displays. Okay. So again, I've got my resting heart rate data here, and the way the stem and leaf displays work is, well, you have a stem and a leaf. Oops. And so the stem is normally the first digit or digits. So for example, if right here, my numbers all stay within the tens digit, but if I had something within the hundreds, right, if I had a data that was 101, maybe you'd pick this as the stem. And then the leaf is usually the last digit, so this would be the stem and this would be the leaf. But with this data, right, with 62, I'm just going to call this the stem and this the leaf. And so for my stems, I can say, okay, well, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. And maybe I don't even need to include this many, right? Maybe I could just start counting at 4 and go to 9. It doesn't matter, but the one thing that does matter is that you have to include the continuous range between 4 and 9 I can't just like skip 5. If I had no numbers that were in the 50s, I couldn't skip the 5. You would have to leave that spot on the leaf blank. Okay. Anyways, so looking at this, like I say, there's no 1s, so blank. There's no 20s, blank. There's no 30s, there's no 40s. Okay, but I do have some 50s. So in here, I want to say, okay, here's a 50, and that's the only one I have, so I'm just going to put 50. There's 54. Okay, so that one's done. Then, now let's look. What do I have that's in the 60s? Well, here's one, here's another, here's another, here's another, here's another, here's another. Okay, there they all are. Yes, 7 of them. And so now I want to order these. Okay, I have a 61. I have a 62. I have, okay, no 63. So I got the 61, I've got the 62, no 64. I have a 65. I have a 66. I have a 67. I have a 68. I have a 69. Okay, so here's the stem, and here are all of its leaves. Then I can go on to 70. So in the 70s, I have this. Okay, so I have 73, and I have 73 again, and I have 77, and I have 78. Now notice I have the two 73s in there. I counted it. I included both of them. I don't want to leave anything out, right? This stem and leaf plot should display all of my data here. And now let's look at the 80s. So there's this one, this one, this one, and this one. So the lowest one here is 84. I have two 84s. And then I have an 86 and an 88. Make this line go the rest of the way down. And then in the 90s, there's just this lone. I have a 98. Okay. And there's your stem and leaf plot, where you've gone through. Oh, there's a 91. Ooh, almost missed one. 91, 98. See, look at that. I almost missed one. That's a 1. Okay. There's my data. I've included every single data point. These are my stems. They represent the tens digit. These are my leaves. They represent the ones digit. And the really cool thing about the stem and leaf plot is if you were to like flip this on its side, you're basically looking at the histogram, right? This is another way of kind of like representing and seeing the data in a histogram form, but I can still see each of the individual data points within or that make up my histogram. So lots of kind of cool advantages of using stem and leaf plots. But that's what this looks like and how we use it. So the next thing we want to look at. Okay, so now for histograms, so when you're talking about, so the biggest thing to keep in mind is that when you're talking about skewed data, this is only for continuous or quantitative data, right? You can't have categorical skewed data because the order doesn't matter. Those are bar graphs. Each bar, they're not connected to the other bars, right? We can't talk about shapes of distributions when you're dealing with bar graphs. That's categorical data. It doesn't matter. But with numerical data, right, this is where we can look at something if it's skewed or not skewed. So here's what I mean by that. So first, so let's say I have a plot. So again, we're looking at frequency versus some value, right? Something that we're looking at. Maybe we're looking at heart rate or whatever. And all of your bars, let's say that your bars look like this, right? You've got a little bar here, and maybe a bigger bar, and a bigger bar, and then an even bigger bar. And let's say you have something that looks like this, okay? Well, if this is your histogram, I can fit a distribution around this, right? Something that maybe looks like this. It goes up and then it curves down. Okay, this is what we would call a normal distribution. And there are rules that determine like if a distribution is like perfectly normal or not, or if it's just a bell curve. And we'll read more about those as we move on. But this is just the thing that we're interested in right now is that if I split this, there's symmetry, right? If I look this way or this way, it's symmetric, right? It's mirror image, right? That's your normal, that's your bell curve distribution, okay? But not all data is really as clean as this, right? What if the distribution looked different? What if it looked something like... okay, so I'm not going to draw the little bars underneath it, but you can just pretend that they're there. What if it looks something like this? What if it's coming along and here's your big bump and then it just came out? Okay, something like this. Notice I've got this huge tail of data on the right end, right? You have a tail on the positive end of your data. Right, so there's all these little data points over here. And these need to be connected if it's really a histogram. So that's what we call positive skew, right? The long tail of data is on the positive side of the distribution, right? You have all of these extra numbers over here on this positive side where the bulk of your data sits over here. There are these ones on this side. And so it skews, right? It pulls your data this way. And next week when we talk about mean, median, and mode, this will make even more sense because when data is skewed like this, it really messes around with where the mean, the median, and the mode of your data are. And that'll be really important for us later. But for right now, we're just looking at saying, hey, this is data that's positively skewed. It has these, and maybe you'd even call these numbers out here outliers. But again, there are rules that we can use to kind of classify and quantify whether or not something is actually an outlier or not. But for now, we're just going to say, hey, yeah, this is a positive skew. So the flip of this, if I take all of this stuff and again, so heart rate, whatever. So what if the tail is over here? So I've got, and then the bump. Okay, so if the tail is on this side, so it's on the negative side of the distribution, right? Bulk of your data is there. Here's the tail over here, right? That's a negative skew, meaning that your averages are going to get pulled to the left, to the negative side, right? That's what this negative skew thing is talking about. Is right. What direction are the averages being pulled? And again, we're gonna dig into this more next week. But we're looking at skewed data. If your tail is way over here, that's a positive skew. Or if your tail is on the negative side, you have a negative skew, okay? And if you have no tail, right, that should be curvy on top. If it's the same either way, right, if it's symmetrical, that's normal. One last type of distribution that you'll see is called bimodal, and that just means that in your distribution, right, you're going along and you have a bump here, and then maybe like there's a second distinct bump, right? Two bumps in your data, that's bimodal. And what that's telling you is that within your sample, right, so you have this population that you took a bunch of samples from, and you have this little sample. That just means that within your sample, there's probably two different categories of people, right? Maybe within this sample, maybe this bump is female, maybe this bump is male. Maybe this bump is seniors, maybe this bump is juniors, right? There could be all kinds of reasons for why there are two different modes, bimodal, within the data that you're dealing with. But that's what that looks like. And I believe that's all I have for you this week. Good luck with all of your studying, and then send me any questions you have. Thanks, everybody. Bye.